Great. So far, we have started this network design course. We started with three important problems. These are like some of the coverage problem, set cover that we talk about it as a very important problem. Then we talk about submodular cover, which is another very interesting problem. And we talked about it. And it is also submodular tree coverage. These are like generalizations that have actually lots of nice applications as well. So now we are continuing that with the maximum coverage problem. And later on, we will also talk about the next problem, which is the unique coverage. But actually, the unique coverage also somehow the motivation came from the maximum coverage. And the unique coverage, I'm very happy about it because I introduced the problem. And it becomes a very important problem as well. So let's go with the maximum coverage problem, or the budgeted maximum coverage. So here in this problem, let me just do this one and then put this one somewhere else. Great. Okay, so let me just do that one. This annotation things taking me some time. Good. Okay. So in the maximum coverage, what is the problem? So, or the budgeted coverage problem? You have a collection of S1, S2 to Sm of cost C1, C2 to C3. So these are the sets. These are exactly the same as input as the same cover as set cover. So we have essentially working with a set cover input for a while. And then we have a universe U1, U2, Un. And each of them have the weight W1, W2 to Wn. And a budget L, that is the total budget that we have. So what is the goal? You want to find a collection, S prime, which is a subset of S. Again, the collection, the same type of output as set cover, to maximize the total weight of the elements covered by S prime, such that the cost of the elements that in our collection should be at most or budget L. So again, maybe just clear our drawings. Again, here, again, it is the case that the input and output is like set cover. We have just some budget L as well. We want to, with total cost L of all the sets that we are selecting, making sure that some of the weights of the elements that we are covering is maximized. So this problem is interesting if all these costs are 1. So all costs are 1. Still, the problem is interesting. So you want to just essentially, and even not only that, but also if the case that even all weights are 1. That is still also interesting. So what is that? That you have a subset. This is exactly set cover with no other additional event cost. You want to find K or L. K and L will be the same essentially. K sets such that the union of them have the maximum number of elements. This problem is the NP hard via a reduction from set cover. Why from set cover? In the set cover, what was the thing? You want to find the minimum number K of sets such that you will cover all the elements. So in the set cover, you wanted to find K such that essentially the minimum K such that S1 to Sk are essentially their union is equal to universe. So here, the idea that why this problem is NP hard, and we knew that the set cover is NP hard, is that K, I mean, you can guess K. So when we say guess, we are hearing a lot in this course. When we say guess the optimum solution, it means that try all possibilities. Of course, here, I mean, we are talking about the case that, I mean, also the cost of the sets are one, but set cover is hard in that case. So K can be essentially 1 to M, but the number of the solution can be 1 to M. We can try all of them. And then like the minimum one that has this property that we can cover everything. I think you can do actually the binary search here if you want to do it better. So if you have a procedure that can solve like the maximum coverage, then you can solve set cover with that, because you guess that see whether with this number K can you, what is the maximum coverage that you have? If the coverage is N, that's a solution. So this problem essentially NP hard. Now let's go and see some interesting things about this problem. This is the part that I need to go to. Good. So we talk about the maximum coverage and the definition. So this was in the lecture notes. I think the student didn't put all the details that now I did. So I want to give a very simple algorithm why this essentially works. And these are like again in this class I try to brought essentially somehow the proof from the book, at least the one that currently exists. So the nicest algorithm that this thing or nicest idea that to solve it, hopefully the simplified one, that you can see the whole idea and you can use it for other research that you have. And here is the one that I want to give. So as I mentioned, let's assume for now that we are considering a simple case. This is the unit case, the unit cost case. That all these guys, all these sets. So what is the unit cost case? So in the unit cost case, all of them have the same cost. So all sets have the same cost. This is the unit cost case. We don't need, we assume that all the weights are one, weights of the elements, but this is the cost of the set would be one. So you want to select K sets essentially to maximize the weight of covered elements. Good. So consider a simple greedy algorithm that picks at each step a set which is maximizing the weight of uncovered elements. This is a very typical greedy algorithm. So at any set, I mean, I have K choices. Start with the one that covers the most, and then the remaining one, and among the remaining one covers the most, and so on and so forth. Good. Now I want to say that this is a 1 minus 1 over E approximation. And then we see what about the generalization, whether it works or not, that is interesting. So let's, I mean, consider opt. Again, when we talk about opt, means that the optimum solution or the weight of it, and we always know, it is interestingly that we know opt. This is interesting. It means that, of course, we don't know opt in real world, but we try to massage opt such that we can get sense of it essentially. And then that's the way that we are designing approximation. Let's consider opt, and let S1, S2 to SL be the sets which are added in our algorithm. So L essentially is the number of, so L is the budget that is given to us. Good. So And of course, I think this is on that we are talking about. So, by the way, S2, you can always assume this one. This is again one way that you can actually write the proofs nicer. We can assume that this S1, S2 to SL actually be the first set, second set, third set, and so on and so forth. It is not necessarily the case. So the order that is given to us, it might be different from this one that we have it. But without loss of generality, you can say that I am ordering the set in this way. That my greedy algorithm, the first set that it picks would be S1, the second one would be S2 and S3 and so on. That's actually a nice way to write it, because otherwise you need to say SI1, SI2, SI3. And that makes the proof essentially just more complicated. You can say that, okay, I'm defining the set this way, and then, especially if opt does not need a different order or something like this. But these are some of the tricks that you may do it and actually improve writing of the paper. The people can get it much nicer. Because if you have one more index, yes, you can add it, but it just adds more to the complications, complexity of the proof. If you can simplify the writing, that would be good. So in this case, let's now define GI. GI be the union of the, essentially the first I sets. So I have S1, S2, and SL. And say these are the, exactly S1, S2, SL is the one that, these are the one that greedy algorithm is doing. And the same index of the thing that is given to us, because without loss of generality, we can change the order of this. Let's find GI be the sum of the I guys of this. And W of a set is just sum of the weights of the elements in it. Good. Now, let's go and try to make clear everything. And this is the best feature of Zoom that I love it. Because with a click, you can clean the whole page. If you write on the board, it takes a lot of effort and dust, or I don't know, things to clean all of them. Good. Okay, so the important thing is this lemma. W of GI minus W of GI minus 1 is greater than or equal to 1 over L W of opt minus W of GI minus G of I minus 1. For any I. And again, GI was the definition of GI. Sum of the first sets that optimum are the same. A union of the first I sets that OR algorithm is doing that. So this is OR algorithm. We call it generally algorithm A. So far we didn't, opt, for opt doesn't matter that much what is the order of that, because just some subsets that has been selected. It's not that important. For us, it is important, the order that we are selecting this guy. So let's define W prime of I be the total weights of elements in SI, the I set essentially that we are selecting, which is by, without loss of generality, I set in the instance that is given, not covered in G of I minus. So, SI essentially is the total weight of elements which are uncovered. If all the weights are 1, that would be the sum of them. We are choosing a set SI with maximum W prime. And the number of sets in opt is also is at most L. Optimum also selects L sets. And again, we don't have any cost here, so we are only talking about the number of sets. What's the meaning of that? It means that if you consider W of opt minus W of GI minus 1, of course, those elements that opt and GI minus 1 are covered by both of them. So that is covered in. So we only talk about the difference. We know that opt has L sets. Each of them, the weight of that, the total thing that can cover, comparing to GI minus 1, would be W prime. So this minus this is at most L times W prime. And note that W prime of I is according to our algorithm, but our algorithm is the one that chooses the maximum. So that's the reason that we have it. So I just replace then W prime of I. What is that? Exactly this formula that we had it. W of, so this is essentially the marginal or in our algorithm. W prime of I is the marginal in our algorithm. W of GI minus W of GI minus. L is the number of sets that we are, the budget. L is the number of sets that opt or algorithm should do it. And again, super important, all the costs are one. So we are talking about L sets. Good. And so this is W prime I by definition is equal to this. So this is the definition of W prime I. And this one, as I mentioned, by this fact that optimum has L sets, each of them can cover at comparing to GI minus one, G of I minus one, it can cover at most W prime. So now we are done essentially. We have this one because then you can just remove this L from here and then bring L here. So this is exactly the formula that we want to prove in the lemma. Lots of these things, it is a correct solution. If you don't see it correctly, it might be very hard to do that. But if you see it the right way, the solution might be actually very cute and interesting. Good. So let me clear everything. Good. So let's go to the rest of it. Okay, so now I wanted to say that this is another lemma that I wanted to prove. W of GI is greater than 1 minus 1 over L to the I times W of opt. Good. So let's try to use induction naturally. We know that the W of G1 is greater than W of opt over L. And if we can just essentially see it, it is trivial as well, because S1 is the one that we are selecting and with the maximum weight. And of course, all opt can have L of such kind of thing, so it would be this. Now, suppose it is correct for I essentially 1 to I minus 1, and then we will prove it for I. What is the W of GI? W of GI is equal to W of GI minus 1 plus W of GI minus W of GI minus 1. So essentially, I'm just adding and subtracting W of GI minus from this. This one I will keep. This one I'm using the lemma one that I have just mentioned. That W of, this was the lemma, if you remember, that was W of GI minus 1 minus this is that is greater than or equal to 1 over L W of opt minus W of GI. Now I will just reordering this one. It would be 1 minus 1 over L W of GI minus 1 plus 1 over L W of opt. And now I'm using the induction hypothesis. So instead of W of GI minus 1, I can just put this formula. So instead of I will just have I minus 1. So I have it 1 minus 1 over L times this times W of opt plus 1 over L W of opt. So I'm just using induction, and everything should be mentioned. This is the equality, so it's just changing the order, simple algebra. And what about this one? Then this is equal to this. I mean, why you can see that one? Because this would be, so that would be, just multiply this one, would be 1 minus 1 over L times 1 times W of opt. And then plus 1 minus 1 over L. Actually, it would be minus here. Again, I have 1 minus 1 over L to the I minus 1, W of opt. And finally, I have 1 over L, W of opt. So this one, 1 minus 1 over L times this. That's the thing that I get it here. So it is 1 minus 1 over L. Now it is, that would be to the power of I essentially. So that would be 1 minus 1 over L to the power of I here. And now this guy, I have essentially minus 1 over W of opt here and plus W of opt here. So this will cancel out this part. And then essentially what remains would be 1 minus this times W of opt. This is exactly the same. So I have essentially, now I have L sets. So this is for I. The last one, essentially, I know that the final thing, this would be GL. GL would be the whole thing that we are covering. W of GL would be 1 minus 1 over L to the L W of opt. And we know this formula that this 1 minus 1 over L essentially, so I think this is always less than or equal to 1 over E. So the limit essentially equals 1 over E. So there, instead of this one, I can just replace the whole thing with 1 over E. And as I mentioned, so I have it minus, so 1 minus over E would be the maximum of this sequence. So I can just replace this. So I get 1 minus 1 over E opt. This is the one that we have. I mean, that's it. Good. Now, this is the question, the things. So let me just do this one. Good. So let me actually go. This part is that was a simple thing that in the scribe note it is mentioned. Nice. Good. So we talk about this 1 minus 1 over E approximation. But the question is that, is this the best things that exist when the costs are non-uniform? By the way, generally when we talk about cost 1 and cost uniform, these are the same for lots of problems. So this is the uniform cost essentially that we could show actually 1 minus 1 over E. What about if the costs are not all 1? Then this algorithm does not work. It's a very natural algorithm. At any time you will take the one that maximizes the remaining thing. Let's see an example. Consider this case that so this is for not general cost function. So consider this set U, which has x1 and x2. And say, actually L, the total budget that we have is P equal plus 1. What are the sets? The first set is x1, and the weight of that is 1. The second set is x2, and the weight of that is P. Good. Now, what about the costs? Sorry, just one thing. So actually it should be here. So this is the weight of this guy is 1, and the weight of this guy is P. So that is the for weight. Maybe forget about weights here. I have already put the weights here. That's a better thing. And then what about the cost? So the cost of S1 is equal to 1, and the cost of S2 is equal to P plus 1. Yeah. What's that? No, for unit cost, this is 1 minus 1 over E. I want to say that if we don't have unit costs, general cost, then this algorithm does not work. So, and can be arbitrarily bad, actually. So consider this case. What is the optimum solution? The optimum solution is that consider just set S2. So if this is the optimum. So the optimum would be just S2. It is a collection, so it would be S2. What would be the cost of it? The cost of it would be exactly P plus 1, which is indeed equal to L. What about the weight of the elements that is covered would be essentially x2, that here we defined it p. What does our algorithm do? So the algorithm is coming, and somehow it says, okay, it just computes. It said that if I just select the S1, the total weight that I'm covering would be 1. And how much essentially cost do I'm paying for that? The cost that I'm paying is also 1. So this is the weight, this is the cost. The ratio of this is actually 1. This is for S1. What about for S2? For S2, the weight would be, the weight of that would be P here. What about the cost of it? The cost of S2 would be P plus 1. So it seems that actually the S1 is more efficient because the cost is exactly 1 versus the other one for S2. Essentially, there's this kind of standardized or normalized weight would be less than 1. So the algorithm actually selects S1, but that's a trap because as soon as it selects S1, then it pays cost 1 for that. Then it cannot select S2 anymore because the budget is P plus 1 and the cost of S2 is P plus 1. So we are trapped and we are done. And here we are selecting. So here the total weight that we have it in our algorithm. So the essentially the alg weight would be equal to 1 versus essentially the opt weight would be P, and this can be arbitrary. Generally, this is the problem for hard-capacitated problems. So what is the meaning of hard-capacitated versus soft-capacitated? This is, again, something that we are hearing a lot in the network design community. So hard-capacitated is this kind of L, that you cannot do anything more than L. You need to pack at most L. The way that the people are doing that, generally they are designing something like things like configuration LPs or others, because it is super important, and all configurations that the weight would be at most L they are considering. Otherwise, this is the event that happens in other things, that because it's a hard constraint, you may make sure that all our algorithm just making mistakes at the beginning and then they cannot recover. Hard capacity means that generally you cannot violate the capacity at all. Sometimes we talk about soft capacitated case. Soft capacitated generally is the case that you can violate, but you need to pay a penalty. Yes, maybe linearly you will pay the penalty. That's the thing that the problems are much easier. Essentially, this is somehow between integer and linear programming. You cannot violate it, or you can violate it fractionally. So this case, it is a hard capacity. It is not easy to, as I mentioned, you need to put some kind of knapsack constraints generally, or more generally, because knapsack is exactly the one that we are putting, such that we will make sure that you can search actually knapsack constraints. So these are some of the things that the people are, this is one approach that is not a trivial one, but you can put actually some constraints for the LP to make sure that this capacity is not violated. Or, as I mentioned, sometimes the people are just writing configuration LPs. In the configurations LPs, the whole idea is that you will consider all possibilities. Generally, writing the LP is easy. Solving it using like essentially solve the LP maybe is possible. It's not that hard, not all the time trivial. Sometimes you may need to use dynamic programming and ellipsoid method. But worse than that, rounding these LPs. These configurations LPs. Very few that we know that it works. Another thing, this is another thing which is generalization of this configuration LPs are generally called essentially LP hierarchies, yeah, or what was just the name? Shirley-Adams hierarchies for the LPs. This is essentially the way that you are putting the variables generally in the Shirley-Adams hierarchies, essentially, or relaxations. We are, this is a generalization of LPs. Generally, that actually comes, the motivation comes from this configuration LPs. That sometimes we will say that, like, for example, object one is there, x1 is equal to 1, or not there, it will be 0. There you are adding more variables. So you will put it x1, x2. You are so instead of considering x1 and x2 essentially separately, you are adding a variable x1 2 that says that 1 and 2 both of them are there, or 0 otherwise. So essentially, that is the concept of hierarchies. Instead of having variables individually, you will essentially put variables that like corresponding that two elements at the same time are there. And it is not just, this is the call, that is the thing that they call it hierarchy. So then not only they put it for 1 and 2, then they will put it 1, 2, 3 for 3 items, or like generally k. This is a k level of hierarchy. So this is again an attempt to build something which is stronger than LP, regular LP. Still, it is an LP. Again, solving them, it is non-trivial. This is like this kind of Shirley-Adams essentially hierarchies or other things. There are other ways, but this is one typical way of all of them. Instead of, as I mentioned, variable for individual variables, you will put it for configuration 1, 2, and then you will put it for all of them. So the idea of this configuration LP is like, what are the current successes of that? The people say that, okay, for example, consider it. So what is the motivation? The motivation, as I mentioned. So there was linear programming, lots of problems that we could solve it, and this linear programming, we could get the best solution. Like, for example, vertex cover, very simple linear programming, you will do it. And we talked about vertex cover because it was a special case of set cover. And we mentioned that you can get F approximation there. F is the maximum frequency, would be for vertex cover would be 2. So you can get a very simple LP and then get it half approximation. But the question is that some progress has happened for some problem like max cut, or somehow the max set, that you can write instead of an LP a semi-definite program, or it is also considered vector program. For them, you could essentially get something better than trivial LP, and you could get essentially for cut, instead of 1/2, you could get 0.78 or 87 something, which is close. So the idea, and then the current state of the art is that SDP is the best. If you cannot, if something you cannot, some approximation factor you cannot get better with SDP, probably you cannot get it for it. Which is, this is also some, how essentially that's the whole unique game conjecture is this one. It's related to this one, so that if you cannot improve something via SDP, then you are done. In some sense, it is like when unique game conjecture was there, essentially, the people, I mean, of course, said, okay, you didn't do anything here, because you say that SDP, we can, the best thing that, the best approximation that we can get it is through SDP. And we cannot get anything better than that, because we can, sometimes the people consider LP and say, okay, if we cannot get something better than LP, probably it is NP hard to get anything better than that. But it turns out it is not the case with SDP. So then there is this attempt beyond SDP, that what else we can consider. So this is the hierarchies, is another example. This is some kind of, or like, there is one, you may write an LP more than one way for the problem. Some of them, the integrality gap are high. It means that these are not good LPs. But you may be able to write another LP. Then the people say, okay, what is a natural LP or natural SDP for this problem? If you cannot improve, this is the best approximation that you can get. And then, but the question, of course, the best doesn't mean that much. So they try to maybe say that, okay, there are some kinds of linear program that if you cannot get better than that, then you are. And there's some relation between these hierarchies and semi-definite programs as well. So you can see one as a special case of others. But anyhow, these hierarchies that the people consider this kind of, these hierarchies in some sense is a configuration LP. Configuration LP comes from this kind of hard constraint that I have mentioned. Interestingly, almost the case, there are very few successes with this kind of Shirley-Adams things that when you put the variables 1, 2, and then you will put it again for everything. However, the way that the people are doing it for a while is that they will write configuration LP for the problem. They solve the configuration LP for the problem. And then configuration LP is non-trivial to get it. But it's still much easier to understand, say, comparing to Shirley-Adams. Then they got the configuration LP. They solved it. They could get some positive results. Then it was a hype in the community that, okay, if I want to present it instead of configuration LP, let's say that the Shirley-Adams is doing that. Lots of the time, when it works with the configuration LP, you can also interpret it as the Shirley-Adams. Like, what is the difference? The difference is that, I mean, configuration LP, you don't put x1, 2 for any stupid variables. In Shirley-Adams, you will put it for every variable. Of course, it is more general because you can put those variables 0. But I mean, if you think about 1, 2, that does not give any intuition how you can solve the problem. How do we get the intuition to solve the problem? From configuration LP? Because sometimes you can write, for example, what's the meaning of configuration LP? Here you want to say you have a variable for all sets that their total cost is at most. That would be a variable that you will put it there. If all of them are there, is 1, otherwise would be 0. But this is the problem. Then 2 variables may intersect because I may put a portion of this as another variable, which is 1, the other. So in some sense, these variables would be very correlated. And that's the thing that makes it hard to round this LP. But essentially, that was the approach that the people took it, essentially. They try to consider this. Let me just see this one. Yes. So, yeah, the people took it, they tried to write the configuration LP. The interesting thing about the configuration LP is that you are going and selecting so you have a very intuitive way to write these variables. That those variables that the sum of the cost is at most L. That's very natural to write it down. In that, and the rounding is non-trivial. But the way that, as I mentioned, the people are doing that, they are doing configuration LP, but to get a more exposure, to get a better confidence, or like say that, oh, by the way, this you can interpret it as a special case of Shirley-Adams, L round of Shirley-Adams, and you can get a better thing. So for a while, it was the thing that, oh, Shirley-Adams can get something better. So if you present it this way, then you had a much better chance of getting the paper. Except I think still it's the case. If you have a configuration, you always try to see whether you can do it Shirley-Adams. But at the same, I mean, it is some kind of weird because really configuration is the one that is more powerful. Almost all cases it has been like that. Even the people may not interpret it, just write it as the Shirley-Adams, but at the end of the day, you start working with configuration LPs. And configuration LPs anyhow comes because of these hard constraints. That you have some kind of knapsack constraint or something that's the best way that you can do it. Good. So this was some understanding about the whole type of approximation. We talked about linear programming and SDP before, but this is something like Shirley-Adams and configuration LP is another thing that used a lot in network design. Good. And so we have seen this one. Now let's come back to our problem. And let's go to this one now. Good. So we talked about it, and I mentioned that, I mean, this is essentially the same example that was written a bit nicely. Here, this algorithm, as I mentioned, our algorithm choose 1 versus the optimum, which is P, and then we are arbitrarily bad. So here, the greedy algorithm does not work. However, you can change the algorithm slightly. We output the best of greedy algorithm. And another thing, that's a typical thing actually that works sometimes. You don't consider one lower bound as your lower bound, you consider another lower. What is another lower bound? You will consider the max of these two solutions, the greedy and the set which covers the maximum weight. So you will essentially, I define the essentially algorithm A prime. So A was the greedy. A prime is the one, is the max of A, and here the max of WS, or S belonging to this callus. What's the meaning of that? Is that you output the max. Either you will consider the greedy solution or the maximum WS, because that's also an output solution. Since you can actually, it's not that hard to show that this is 1/2 approximation. 1/2 times 1 minus 1 over E. The general idea is that essentially it says that consider the optimum algorithm when this problem that I mentioned happens because of the last guy. Because the last guy, optimum, can do it nicely, I cannot do it. So here I will do two things. Instead of consider the max of this guy, optimum in some sense can get the sum of these. I cannot get some of them because they are inconsistent. Either I can get the max guy or the all previous guys. So essentially I'm using another factor 1/2 here. 1 minus 1 over E because of the greedy. But another factor 1/2 because, again, optimum takes both the last guy and the previous guy. I can take either the last guy or previous guys, which is 1 minus 1 over E. So then essentially you are losing a factor 1/2, and then you get 1/2 minus 1. However, there is a paper. This is actually a beautiful paper. So this is. Yes. So this is a beautiful paper. This paper. This was actually in the information processing letter. This is actually the old journal. It's a nice one. These are the people are publishing. I think you can have at most 8 pages essentially in the journal version. In some sense, was there are lots of nice results, cute results, simplifications before the old journal. Maybe the people now are sending to some other conference, etc. But this is a very nice one, and they actually prove there lots of this. In this paper, they show that even for the general weighted case, so as I mentioned, so far we can get 1/2 minus 1 over E. The question is that can we get 1 minus 1 over E or not? In this paper, actually show that yes, a little bit more, careful. You need to change a little bit the algorithm, but then you can get, instead of this, you can actually get 1 minus 1 over E for general cost as well. But this is non-trivial. It's not a trivial algorithm. 1/2 is easy, but not the essentially I mentioned the proof. 1 minus 1 over E is non-trivial. It's not that hard, but it's cute. This paper, you can read that. Now let's go and and essentially, you see, this is again some type of configuration, but this is the algorithm. So fix an integer k greater than or equal to 3. Then the algorithm essentially is to output the maximum weight of 2 type of candidate solutions. First is that consider all subsets of S of size at most k that have cost at most L. Note that in the previous case, I mentioned that I will just select one set that has maximum weight. Here I'm saying that, okay, in the algorithm, I can do it more than that. I don't need to consider one set. I can consider all, like 2 sets that their size, sum of their cost is at most L, and they cover the maximum set of elements. So algorithmically, I can do it. For any constant k, I can do that. Good. That's the first one. The other one is that consider all subsets S of size k, which have cost at most L, and then complete each of them to a solution using the greedy heuristic essential. In some sense, actually, I think this is the thing that is written for this. I think this form is somehow is more general than the previous one. So you can actually keep just this one. Consider all subsets of size k that their size is at most, their cost is at most L. Good. And then extend it using the greedy algorithm. I mean, for the analysis, you may consider them separately. But for the algorithm, I can just mention that consider all subset of k. For any k, you can try that as long as k is constant. All k, their size is at most L. And then if you can add more things to them using greedy, do it. For the analysis, you may consider them separately, those greedy type of things and this. You see, this is the generalization of this previous algorithm that I mentioned. For any k, when k becomes essentially large, if k is equal to 1, it essentially says that take the maximum weight guy that covers the maximum and then run the greedy after that. Instead of just greedy, take the greedy. But this algorithm, actually, you can show that it is 1 minus 1 over e. I'm not so sure that there is a plus epsilon there or not. You should check that. But that's essentially the things that we know. So this is a very natural algorithm again. And this is, again, another interesting thing. Lots of the time, this type of algorithm, when you get it that you will try the max guy or something like this, a generalization is that algorithmically, you are not forced to take only one guy. You can take 2 guys, 3 guys, k guys. And as long as k is constant, algorithmically, you can try that. And you get a polynomial time algorithm. And then sometime, actually, you can get better as you see that. Instead of 1/2 times 1 minus 1 over e, you can actually go to 1 minus, or I think close by. Anyhow, you can read all the details in this paper, the paper 3, which is a very important paper. It's got lots of citations. Last but not least, I wanted to say something also about this algorithm, which is also interesting. So the question so far, we have discussed that. So far, we have talked about 1 minus 1 over e for this maximum coverage. And first, we mentioned this one for the unweighted case. Like not unweighted, like the cost that all the costs are the same. And then said that actually you can get it 1/2 times that, and you can using this greedy algorithm that gets k sets instead of 1 set, and then run the greedy, fix k sets, the best sets, and or k sets, and then run the greedy. Then you can get actually 1 minus 1. The question that can we get better than 1? And this is actually a simple algorithm that we are doing here. So we discussed this theorem. We are using this theorem of Feige, and I think there is some better versions of that, if I believe that. So even in the unit cost version of the maximum coverage, even unit cost version, one cannot get the problem better than 1 minus 1 over e unless NP is a d time deterministic time n to the log. So this is NP, I mean, it's not equal to P essentially, versus here, it's okay, it's a little bit more than that. You see that NP, this is a bit somehow a stronger assumption, because this n to the log n is not polynomial. Generally, we say that NP is not equal to P. But here it says that, I mean, NP is not even a subset of n to the log. N to the log n is larger than polynomial. So here, of course, we know that P is a subset of NP. So the typical assumption is that P is a subset of NP unless this. But here we have unless NP is the deterministic time n to the log, and a little bit not polynomial. NP even is not subset of slight or a little bit more than polynomial. And a little bit means n to the log. This is a stronger assumption. And as I mentioned, you can actually, I think you could get, and this is exactly, so here, this is the first thing that it comes is from this paper of Feige. He said that the set cover problem, so this is the set cover problem, is approximate, I mean, within a factor of 1 minus 1 over e. So this is the set cover. I think just make sure that this good. So this is the set cover. The best factor that exists for this is 1 minus so this is, so you cannot get anything better than ln of n, and it is ln. This is exactly, because the constant is important here. I want to say that you cannot get, so for set cover, maybe, okay, ln log, there is no difference. Still, they are order of log. But for this problem, maximum coverage, the constant actually is important. So the constant comes from the fact it is ln of n. I think there was, there was some papers that you can prove that this the set cover does not have 4 times ln of n under the assumption that p is not equal to p, not this stronger assumption. But then there was this result that you cannot get better than 1 ln of n under this assumption. I believe there is some progress, and it might be the case that now actually we have it, that you cannot get anything better than ln of n under the assumption that p is not equal. I think that has been improved, but you should check that one. But anyhow, it doesn't matter that much. So here it says that for set cover, is you cannot get better than 1 minus epsilon times ln of n, and the constant is ln versus log is important because that changes the solution. I want to use this, so this is for set cover. But note that from set cover is log n. From that, or ln of n, from that I want to get some constant lower bound for set cover, for this maximum coverage. So again, this is some kind of reduction. This we talk more about this other course that we have, algorithmic lower bound assumptions and reduction. This is the assumption I want to give a reduction. How can I do that? He said that, okay, if I can, so I want to say that if this kind of, and this is correct, this set cover, even for the case that the sets are unit cost, essentially. You want to find the minimum number of sets such that their union is at most, so the union covers everything. Here also I consider maximum coverage, all the costs are 1, and I think even the weights you can consider 1. I want to say that you cannot get better than 1 minus over e approximation. Assume I can get it. So I want to define a new algorithm for set cover. So what is this new algorithm? Consider the unit cost set cover, assign unit weights to each element. So we are essentially considering the set cover things, and all the weights are 1. And we know that according to Feige, we cannot get better than 1 minus epsilon ln of. So assume that there is an algorithm A that approximates with a factor alpha greater than 1 minus 1 over e for, let me actually do this one, clear everything. Then let me just, that might be a bit better. Good. So, and consider an algorithm A with approximation factor alpha greater than 1 minus 1 over e, or like I will say better than 1 minus 1 over e here. For maximum coverage. Again, for maximization problems, sometimes the people use half approximation instead of 2 approximation, but always we say, I will say better, it is clear. Better means closer to 1 versus far from 1. But then you can get better than 1 minus 1 over e. What do we do? Guess the number of sets in the set cover instance. So I want to create from this algorithm A an algorithm for set cover. Okay, set cover problem. I know what is, I can guess the solution for the set cover. Again, no weights, no cost. So the solution would be K. What's the meaning of guess means try all possibilities. So, and say that for a party, and then take the best solution. Say the solution has k sets there. So I know that the number of elements which are covered by k sets in these things is at least n by definition, because I know that there is a solution of size k. No, this is the new algorithm that I will do it for setcover. I will run A. Okay, so I'm giving the same K. This K, the maximum coverage problem has a K as an input. I will give this K to that I guess from the setcover, so that find the best solution that maximum. Of course, if it covers everything, I am done. If not, I will repeat with the rest of the elements. So I cover some elements, I will delete them, say that, okay, now find another K set for. Then get all the things. You will do it until, reiterate, until all elements are covered. Good. So assume that this algorithm A essentially. So this algorithm, we know that the approximation factor of this is alpha, which is greater than, essentially this is better approximation than previous case. What's the meaning of that? I think the approximation factor actually is really 1 over alpha. But anyhow, because we are considering greater than 1. Here, it means that this algorithm A can cover alpha n. Note that at any run, there is always k sets that they can cover everything. Good. There is, in each iteration, there is a k set that they can cover everything. So it means that, but in general, what's the meaning of this algorithm? Because there is a solution of size n that can cover everything. I know that this algorithm A, the solution that it gives to me, it should cover alpha n elements. That alpha should be better than 1 minus 1 over A, because there is a solution of size n. Good. Now, so this is the only thing. You will do that, you will run it, and then you will do that. And this is important, that each iteration, there is a solution of size k. There is a solution of size k that covers n. Good. Now let's do I want to say that this algorithm would be something better than ln of n approximation for set cover, and then I get essentially the proof by contradiction. Okay. So let's, the number of uncovered elements at the start of iteration I be ni. Of course, at the n1 is equal to n elements. So this algorithm covers alpha ni with k sets. So I know that, and again, at each iteration this happens because those original k sets of the solution always a solution in each of these inputs. So I know that ni plus 1 is less than or equal to ni times 1 minus over alpha, because it covers at least alpha fraction. So the remaining item would be less than the previous guy times 1 minus. Good. So it means that if we iterate L plus, say that this algorithm essentially, so how many, and we know that the solution to the greedy was k. For the solution for the set cover was k. So say we are doing this algorithm L plus 1 times, and we know that NL is greater than or equal to 1 by definition. Otherwise, we didn't do the L plus 1 iterations. So this algorithm is doing L. I mean, L is the number of things that is covering. And of course, the total number of things that it covers would be, I don't know, say L plus 1 or L times K versus, I mean, let's say L K versus K. So that was the optimum was K, or algorithm is doing it L times K. So we have the approximation factor L. And I know that we are doing L plus 1, but we know that at least in NL, it was at least 1. Because otherwise we didn't do L plus. But these are just 1 does not change anything. Okay, so let me clear everything, and then I think we are in a good shape now. Just write some formula, and then we are good. Now, I know that NL is greater than 1 here. So what do I have? I have NL greater than 1, as I mentioned, so because we are doing L plus 1. And I know that NL is less than or equal to NL minus 1 times 1 minus alpha, because of it is the alpha approximation, and this is the one that we done. So I just expand this one, NL minus 2 to this, and so far N to the 1 minus alpha to the L. So I know that thus I have it N times 1 minus alpha to the L is greater than 1. It means that L is less than, I just solve this equation, the last one and the first one. And then I get L is less than Ln of N times this. Good. So what's the meaning of that? Does the set cover, so I know that my set cover has size KL. And here, as I mentioned, L is at most this. It would be K times Ln of N, Ln of this 1 minus 1 over alpha. And K, I know that the optimum solution for this problem would be op times Ln of N, Ln of 1 minus. Good. So the number of sets that I will find would be opt over Ln of N over this. Now, I knew that, so I assume that alpha is greater than 1 minus 1 over E. It means that 1 over 1 minus alpha is greater than E. It means that Ln of these things is greater than 1. So it means that this denominator is greater than 1. So it means that I could get a better algorithm, which is a contradiction to Feigel's theorem. So these clean things, and again, these are like you need to see it the right way. Otherwise, it would be non-trivial how you can get a hardness for this problem using this problem. But when you see it rightly and you define it, actually you can get it nice. So this also you cannot get it better than 1 minus 1 over E. So here essentially, and this is other one, generally there is this kind of this problem maximum coverage. This is a special of, submodular maximization essentially, that you can read about it, and there's a lot of work there, and there is also that 1 minus 1 over E is the tight things there. And there are like a generalization when everything almost when we are considering weights, whenever the weights are linear, we are summing the weights for the elements that we cover, and we are summing the cost for the sets that are there. As soon as these are essentially linear, you can think about the other two versions. This is the submodular or subadditive version. And this is very natural. And again, that comes because of economies of scale. So this also we hear a lot. Why economies of scale? Because whenever this is submodular or subadditive, subadditive will be harder. If we can get it, that would be better. But submodular, generally, we can get it. That's the thing, that there are lots of papers on submodular, much less on subadditive. So the whole idea is essentially economies of scale, that it is in submodular or subadditive is there. And the idea is that if you buy more, there is a discount for it. If you go, for example, to Home Depot, you want to buy things, they explicitly say, so that if you want to buy individually, this is the price, but for $1, essentially, if you say, I don't know, then they say, if you buy 10 items, then I have a lower price. It is a very official thing, economies of scale. And that's the reason that the people consider. So here I will say, okay, 2 sets, 3 sets, maybe I get 4 sets, I should get some discount. That's the thing that the people consider it for submodular or subadditive. So any problem you will consider it naturally, you can consider submodular or subadditive version of that. And that is non-trivial, essentially, to get it. Sometimes you can get the same thing with additive, not all the time. Good. So this is for this one. And finally, last but not least, we have covered set cover, we have covered maximum coverage, and I mentioned these are submodular versions of each of them. The next problem that we are considering would be the unique coverage. Next time we will talk about it. And in the unique coverage, essentially, the goal is that, again, the input is a set cover instance, but we will count the number of elements that are covered by our sets. Exactly one. If it is 0, we don't count it. If they are counted more than 1, we don't count it. And this is, again, we are considering essentially in the wireless network case, for example, we consider those areas that are covered exactly by 1. They have a coverage, and they don't have any interference. Because if there are 2 sets are covering, there is some interference. We will talk about it. This is non-trivial. Again, I'm happy that because I introduced that problem, and it was somehow at that time that he introduced it, oh, maybe some solution like this should work, but it turns out none of this solution works. And it turns out the unique coverage is probably the most natural maximization problem for which there is no log n, there is nothing better than log n approximation. Versus set cover, which is the most famous problem, essentially minimization, that there is no log n approximation better than log n, is set cover. For maximization, unique coverage, there was no such problem before. There was one actually domatic number. It was not that natural. It was actually with Arvind, Srinivasan, who is a professor here. Anyhow, I think I end here, and then we will talk more about this next sessions about the unique coverage and the rest of